Okay, so let's get going. First of all, I'm very happy to see so many people here. I kind of expected to be here with 3 people, but apparently there are people without suits on this event, so these seem to be the technical people. And yeah, sorry about it being so cold here. I freeze too, but not much we can do. So let's get going. We will be talking about SUSELinux today, which will be the new mandatory access control system on SUSELinux. I will give you a brief introduction, first myself, then my team. Then I will tell you about the basics, how SUSELinux works, which is a pretty complex system, so obviously I can't really dive into details here. Then I will tell you why we actually did the change. And then I will explain to you what this means for you based on some scenarios. Good, let's get going. So, my name is Johannes Segitz. I'm a security engineer. I work at SUSE in Nuremberg in the headquarters. I do code review, although I mostly lack the time for that nowadays because you need a lot of uninterrupted time for that, and that's kind of tricky for me. I do product pen testing, so before we release a new SUSE product, I look at it from an offensive point of view and try to break it. I'm an SUSELinux expert, that's the reason why I'm standing here. And I'm also the lead of the engineering red team, so we have a team of interested engineers that do internal attack simulations. So we try to break stuff before other people can do that. And I work in the SUSE product security team, and that's an important distinction. So by now we have a couple of security teams within SUSE, cybersecurity and for certifications and whatever. We really take care for the product security itself. And since we are a pretty big team by now, I think we have like 17 people, we are split up in 2 groups. We have the reactive security, which does mainly incident handling. So that is the classical security issue handling that you all know. Security vulnerability is discovered, CVE gets assigned. We analyze all of that, we check how to fix that, and then we release an update. And we do that for SUSE, but also for OpenSUSE, which extends our scope pretty wildly because they have a lot more packages. And then the proactive security group, which I'm part of, there we do all of the work that we do before shipment. So code review, hardening, all of the work to then hopefully be not affected later on by security vulnerabilities or reduce the blast radius as far as possible. But of course there are certain limits to what we can do because all of you probably have different needs for an operating system, and if we just lock it down as much as possible, then a lot would be unhappy with that. It's mostly a fun place to work unless someone discovers a backdoor right before the Easter holidays. So I assume all of you have noticed this exec thingy. That sucked. So please, if you discover something like that, tell us on a Monday. Then we have 5 work days. Yeah, that would be great. And also the kernel team unfortunately now is a CNA, so they can issue CVEs, which they do a lot. I think 1,000 last month, something like that. And then if we have to analyze them, that's kind of like a denial of service towards us, so that is tricky. So let's dive into the basics for SUSELinux. Before we can discuss SUSELinux, we need to talk about the traditional way of access control, which is called discretionary access control. So I assume all of you are familiar, that's the usual way of access control on Linux systems and a lot of other Unix systems. And we see a typical example here. So we have the etc shadow file, and we see it belongs to the root user, the shadow group. And then we have these bits that specify that root can read and write, members of the shadow group can read, and everyone else can't do anything on that file. And I know there's a little bit more. There are setuid bits, and you can use access control lists, but that's mostly the basis for securing a Linux system. And the discretionary part here stands for the fact that you as the owner of a file can control access to the file. And that might seem very natural, but it's definitely not the only way how you can do access control on a system. And it also has a couple of drawbacks. So first of all, this form of access control is pretty coarse. You have these 3 bits for the user, the group, and everyone else. So it's not like you can do very fine-grained control with that. It's also prone to user error. So if you look at this, for example, here I just changed my private SSH key to be readable and writable by everyone on the system. That is a really bad idea, but nothing stops me from doing that. No? In this case, the OpenSSH client will complain about these permissions and at least tell me, But in other cases, nothing will tell me. I will notice when someone else tells me, and that's usually then, or when I'm lucky, that's a nice guy. When I'm unlucky, this is someone that wants money from me. It's also hard to analyze those permissions. You have a couple of problems. So if you want to reason about the security state of your system, you first need to collect all of this information from your system. So you go over the disk and get all of these access bits. But there you already have a race condition. So when you finish with that, the state of your system could be different than what you're currently analyzing. So that's kind of a problem. But even if we ignore that for now, then you still have the problem that you are working on low-level information. And you are not really talking in a high abstraction, so it's hard to reason about the security properties of your system. That makes it really hard to work with that. And then you have the fact that root is basically God on a Linux system. We have capabilities to work around that a little bit, but half of these capabilities are full root anyway, and the other half is not that useful, so yeah, tricky. So now let's jump into mandatory access control, and the operating word here obviously is mandatory. So that means that access control decisions are not made by the owner, but you have a central policy in which the rules are managed in a central way. And that has a couple of advantages. So first of all, you can put access control in the hands of people that know what they're doing. You can, of course, put it also in the hands of amateurs, but I would recommend putting it in the hand of experts. And it also makes control and review rather easy. Because if you have a server running and you know that you installed a new policy a week ago and plan to update it next week, then you know that in this time frame, access control is done by this policy. There's no change because the policy is unchanged. And it can also be very fine-grained. So most people don't need it to that detail, but there are organizations that, for example, use security clearances. And let's say the whole room here is now top level cleared, but we have a certain mission and only this part of the room is going on to the mission. Then we can ensure that only this part of the room gets the top secret information and everyone else that does not have a need to know does not get the information. That's usually not the level of access control that most organizations need, but if you need it, then it's possible with SUSELinux. It also, with like almost everything in life, has a couple of disadvantages. You rarely get something for completely free. It is harder to understand, and you will appreciate why after my talk. It is more complex to administrate, which is kind of self-evidently true, because you have an additional layer that you need to manage. If you don't use a mandatory access control system, then, well, your life is rather easy, probably also rather insecure, but it is just an additional thing that you need to manage. And the main topic really is the missing experience. SUSELinux is not something that you learn in 5 minutes. You will also not walk out of this room and understand SUSELinux, and it is a different way of thinking. And this is, in my experience, the main problem for most users. They first of all need to realize that they actually have a problem with SUSELinux, which can be tricky. And then they need to understand how SUSELinux works. And this is a skill that requires some time. So why do we do it then? In general, it really increases overall security. I also work as a pen tester, and when I break into a system and it is SUSELinux enabled, then I'm rather annoyed. Depends a bit on in which context I come out, but if it's a restricted context, then I can do very little. And if I just do one mistake, then suddenly the logs will be very noisy. So that is really a pain, which of course, from our perspective, good. And it also solves some of the issues that we have with modern operating systems. So you all know that operating systems that we mostly use today come from a time where security was not much of an issue, and you notice that. So your browser can access all of your financial data that is stored on your disk. That's not really a good idea to do it like that, but that's just the way modern operating systems work. If you have a mobile like Android, then you see how it can be done differently. Every app there, for example, runs on its own distinct user, and you only have some gateways in which you can traverse the system. So that's the way how you would build a system today, but we live in the world that we live in, and SUSELinux, at least to some extent, allows us to work around these design issues by fitting a tight harness around processes and try to keep their privileges as minimal as possible. So that's basically the main idea of SUSELinux. The main idea of SUSELinux is type enforcement. Every object on a system has a user, a role, a type, a sensitivity, and a category assigned. And if you put this then all together, then you get this nice colorful string here, which is a so-called security context. And you do access control from one security context to the other. And now this looks pretty intimidating in the beginning. Let me say two words. So first of all, the sensitivity and the category, you don't see them always because they are not used always. And also, especially in the beginning, just ignore everything apart from the type, because the type is the important thing for access control in SUSELinux. The other things also are needed, but especially in the beginning, you can just ignore it. You will likely not have much problems with that. And the type usually also ends with a suffix _t. That is not necessary, but it's convention, and usually you can easily find out the type. So if you see a long string like that, forget everything, just look at the type. Pretty much everything on an SUSELinux protected system has a security context assigned. So sockets, packets, there are over 130 different security classes, and you can do a lot of fancy things if you want to do them, but mostly you will just see them with the normal objects that you normally operate. So if you add the capital Z command line flag, which is the one thing, if you remember one thing from the talk, remember capital Z. That is like the main important flag for SUSELinux. Then you will suddenly start to see all of the necessary information for SUSELinux. So again, we list the etc shadow file and we add our capital Z. So now we see the security context that is assigned to etc shadow. And as we just learned, we ignore everything and just look at the type. So etc shadow has the type shadow t. If you look on your system and you see different security contexts, then always try to think if the type that you see here matches the object that you're currently working with. So etc shadow with the type shadow t, that kind of seems to make sense. If you see postfix t as a type, then your system probably will break pretty massively. So these types usually correspond pretty well to the objects that you're looking at. Same for processes. Again, magic capital Z flag. Here I grabbed for the postfix master process, and then I see the postfix master runs as postfix master t. Again, makes a lot of sense. If you see something different, if your SSH daemon, for example, suddenly runs as kernel t, probably not a good thing. When you look at a system, then first you will always have discretionary access control. So if an access is forbidden by discretionary access control, then SUSELinux will not come into play. We just saw the example with etc shadow. So if I, as a normal user, try to read etc shadow, then already discretionary access control will forbid this access, and SUSELinux will never see this. So you will also not see a denial. After that, after DAC said, fine, you can do that, then SUSELinux comes into play, and it's a denial by default system. So it's basically like a well-configured firewall. You also don't have statements to really forbid anything for SUSELinux, because you just don't allow it. There are some never allow rules that you can use, but this is a bit more of an advanced topic. And it's basically like a firewall for system calls. So pretty much always you have a really good correspondence between the system calls that a process does and the SUSELinux permissions that it needs. So it wants to read a file, or it does a read syscall on a file. You need a read permission on file objects in SUSELinux. It's not always one-to-one, but it is pretty close. And usually you try to think of subjects doing something on objects. So here we see one security context, and this is a typical example for an unconfined security context, because user sessions usually are unconfined in SUSELinux to make living with SUSELinux easier. And here we see the subject tries to do something on an object, and here the type is unfortunately a bit not that greatly named. So this is a virtual machine. There are some historic names in the policy that are not that great, but we can't easily get rid of them. and it does certain operations. And this is also one of the examples where the categories for once are really important, because with virtual machines you have one type, and if you now have 10 virtual machines, they would all share the same type. And that would also mean that they all share the same permission, but that's not what you want. You want to also separate your virtual machines. And that is then one of the few cases where the categories become important, because then you assign different categories, and then you can separate these different VMs from each other. If you want to run SUSELinux, you need a policy where all of the rules are written into that then regulate access on your system. We will now provide on every system where we will use SUSELinux also a policy. That's the big difference compared to previous SLES versions, because you can also run SUSELinux on SLES 15 if you like to, because the kernel understands it, the tool chains are there, all of the libraries have the necessary support, but you don't have a policy from us. And writing a policy yourself is not a small task, so it's better to wait for the newer versions. And they usually come in 3 different flavors. So we have a minimum policy, which only constrains part of the system. Then we have a targeted policy, which constrains pretty much everything in a system. That's also the default policy that we will be using. And then there's an MLS system, which stands for multi-level security. So those are the freaky guys that want to do like top secret clearance, whatever. But this is not useful for most people. This policy consists out of different modules that you can dynamically load and unload. Currently, we have around 440 modules, so that's already quite a number. And these policy modules can be written either in basic SUSELinux statements, which you should really not do, because that is like programming in assembly. I mean, some people have to do that, but most of the people really should not do that. Or you can use the abstractions that the policy itself provides. So the policy has a couple of interfaces, and you can use these interfaces like function calls in a programming language, and then you have a certain abstraction. And we will see an example here, and I will not really show you a lot for the low-level policies, but just that you have seen this at least once. So this is the policy for ARPWatch. ARPWatch is a daemon that listens on the internet, on the network interface, and it detects certain attacks on a low level in the network. And we start with a name, so we say this is the policy module ARPWatch. We give it a version number, and then we declare 2 types. So we declare the so-called domain type. This is the type in which the process will be running, and we call it ARPWatch-T. So again, pretty good correspondence between the daemon name and the type itself. And then we have the executable files on the disk, and they need to have a distinct type. And therefore, we create also an additional type, ARPWatch-exec_T, for the executable files. And what we now need to do is, we need to tell the system, if you execute a file of ARPWatch-exec_T, then please transition into this new domain type. And that would require quite a number of rules, and you would also repeat yourself constantly. It's error-prone, it's not a good idea to do that by hand. And therefore, there is an interface called init daemon domain that tells the system if the init daemon, so mostly systemd, executes a file tagged with ARPWatch-exec_T, then please transition it into this type. And this is a pretty common pattern, so you see something like that a lot in SUSELinux modules. And that really helps you to, first of all, not use any low-level details that might change, but also just keep your policy a lot smaller and readable. Then we define a type for our own data files, because a lot of daemons have private data that they want to use only for themselves, and therefore we need a dedicated type for that. So these will be a type for files on the file system. And now let's assume you have a backup software, or maybe you're a vendor and you're writing a backup software. If your software needs to run on an SUSELinux-enabled system, then you need to have rules that allow you to access all of the types that are associated with this file system. And you can't really know all of them, because there might be some random module written by a customer, or maybe this customer has like 200 modules loaded, the next one has 300 modules loaded. It's very complex to do this. And therefore, the policy provides you an interface file type, which allows you to declare your type as a file type, and then there are again interfaces that allow you to do something like, let me read all files on the system. And you don't need to know which file types there are, because the policy does abstract all of that. This is then handled for you. And the thing is quite a bit longer. That's the only thing that we will be seeing here. Like the AppWatch module is also a good one to check if you want to see a bit more of that. The Apache module is not one that you should check in the beginning, because that's over 1,000 lines. So depending on how complex the daemon is, usually also the SUSELinux module is a lot more complex. Initially, you need to label your file system, because when you install initially, then all of these types are not associated with your file system. And this is also done by rules in the policy. So you have a regular expression. It can be just a plain path, or you can use an arbitrary regular expression. And then you specify which kind of type you want to associate with that on the file system. So unsurprisingly, our binary for the AppWatch daemon gets the type AppWatch exec_t. So initially, when you have your system and switch to SUSELinux, then the whole system is relabeled. All of these types are set. Once you do this and have already an SUSELinux enabled system, then RPM will do this automatically for you. So it will consult with the database and will set the types accordingly. If something goes wrong with SUSELinux, then you see SUSELinux denials. And you will definitely see SUSELinux denials. If you have an audit daemon running, which I hope all of you have, then these will be in the audit log. And they look like that. So I broke down the line a little bit because it is quite a long line. They are of type AVC, and you see something got denied. We see that the permission that was denied was a transition. Then we see, okay, it has something to do with the SSH daemon and a shell. And then we see a source context and a target context. So subject and object, what we saw earlier. And then we have a security context again, but we ignore everything apart from the type. So we see the source is kernel T and the target is unconfined T. And we did all of this on a process. No? And reading those denials needs quite a bit of practice. But usually you can get quite far just by thinking logical about this. So we see that the SSH daemon is involved here in some shape or form. But we see that the source is kernel. And in this case, it was a pretty simple mistake. So the kernel launches the init daemon then launches the SSH daemon, and somewhere along this chain it broke, and because of that the SSH daemon ran as kernel T. No? Not something you will learn in 5 minutes, but over a while you get a certain feeling for certain denials, why they happen. It just takes a bit of practice. So how do you handle denials? So the first step that you should definitely do is consider what you're doing here. SUSELinux is a security system, and if your security system screams at you, your first reaction should not be, how do I get rid of this? You also don't go to your firewall logs and just allow blindly everything that you see in there. From time to time, of course, the policy has bugs, but sometimes it's also an indication that what you're doing is not a good idea. Also, quite often, some files are just labeled wrong. So especially when you use non-default location for your files, then you probably just need to tell the policy about how to label those paths, and then most of the time that solves the problem. That's probably like 80–90% of SUSELinux problems that you're going to see. Something is at a different location, SUSELinux does not understand it, you need to tell it, and then everything is fine. Then there's a tool called audit to allow, which we will cover on the next slide in more detail. This tool takes the denials and gives you then the necessary permissions to not run into these denials again, but we'll cover it more on the next slides. If you're already deep into the debugging mode, then you can switch your system into permissive mode, which means that SUSELinux will not be enforced, but you will still see the denial messages. That's a really good way of figuring out if SUSELinux is really a problem. Because if you can reproduce the problem and you disable SUSELinux or set it to permissive, then and the problem goes away, then very likely your problem is SUSELinux. And you can do that either system-wide with set enforce 0, then SUSELinux is disabled on the whole system, you will be allowed to do everything. or you can just do it for a single domain type, and that is usually the way better idea because you don't want to remove all protections from your system. So let's say you have a certain problem with OpenVPN, and OpenVPN has unsurprisingly the domain type OpenVPN_T. Then you can, with SEManage permissive, set just this type to permissive. That means the whole system is still protected, just OpenVPN will run in permissive mode. And of course, you can always open a bug, but if you do that, then please tell us how you created the problem, and also add the denial messages, because some people just send us bugs like stuff is broken. Okay, yeah. Good. Audit to allow. Very helpful tool. It takes these denial messages. You can either read them directly from the audit log, or you can just paste them into stdin. And it will then generate the necessary rules that you need to prevent these problems going forward. The really nice thing about it is aware of the policy interfaces. So it will by default spit you out the raw rules. But if you tell it to use the interfaces, then it will figure out which interface to call and will give you a much cleaner module. And you can also use it to directly compile these rules into an SUSELinux module. It will tell you how to load it, so that makes it really easy to fix these problems. It also suggests you booleans that will allow a certain access. So the SUSELinux policy is aware that certain workloads need different permissions than others. And the prime example usually is a web server. Especially in universities, you quite often have a directory in your home directory. You can place files in there, and they will suddenly appear on some web server. That requires the web server to read your home directory, which is not something you usually want, because if someone breaks into my web server, I don't want them to be able to read my home directory. But for this use case, it's useful, and therefore there are these switches that you can toggle and change the behavior of the policy. And audit to allow is smart enough to understand these, and if it sees, well, you could just change the switch and your problems go away, then it will tell you that. No? So that's quite a nice feature. And yes, it is very, very helpful, but please don't just use it for everything. I've seen people run loops that just scan the system log, compile these modules, load them into the system, and then everything worked. Yeah, of course. It's like you drive with your car, you hit a tree, and instead of thinking about maybe your driving wasn't perfect or the weather or something, you just buy a tank and go over trees. I mean, yeah, that works, but that's not a solution. And it also makes SUSELinux Kitty really, really sad, so please don't do this. It's the only picture in my presentation. Good, let's talk about the motivation. Both systems, AppArmor and SUSELinux, are good mandatory access control systems. Both have advantages and both have deficits. SUSELinux definitely has seen more traction over the last couple of years. So there are more people using SUSELinux, especially on the policy part. There's a more active community that works on these policies. It is, for example, the default mandatory access control system on Android. So if you have an Android phone, you're an SUSELinux user. Likely you did not notice any problems, unless you try to root your Android phone. Then it becomes a problem, but it's the job of the system to prevent that. Especially in high security environment, SUSELinux just offers more. You can do a lot more, and the confinement in general is tighter and better from a security point of view. The drawback, obviously, is that SUSELinux is more complex. So I had a talk a while ago where I compared both systems and showed people AppArmor policies and SUSELinux policies. And if someone did not have any contact with these systems before and gets in touch with AppArmor first and has a decent Linux background, then I will probably be able to explain to him AppArmor in an hour. With SUSELinux, you just need a lot more practice. But it is definitely a good system from a security point of view. I absolutely hate it when I hack something and I end up in an SUSELinux-enabled system. That just makes my day really bad. And the policy that we ship has really, really good coverage. So the AppArmor modules that we had were mostly focused on network-facing daemons. And that was already quite good because that is basically a lot of your attack surface. But SUSELinux covers a lot more of your system. And especially now with threats that are a lot more advanced, it is definitely a good idea not to concentrate only on the network-facing parts, but also have defense in depth on your system itself. So let's go to the interesting part. What does that actually mean for you? You will need some basic SUSELinux knowledge no matter what. Unless you disable SUSELinux, but I would really recommend not to do this. No? That will require you, if you're in a technical role, to understand that, and will probably also require your colleagues at least to understand it to some extent. Not everyone needs to become an expert, but you need to be able to figure out that you have an SUSELinux problem, and then it probably really helps out that at least one person has a little bit more knowledge to be able to debug the simple stuff, and then for the more complex stuff you can come to us. And now let's look at a couple of situations. So if you just used plain SLES with the existing profiles, then migration will probably be really easy for you. Yeah? You just change to a new product, you change from AppArmor to SUSELinux, and we will make sure that this does not cause problems for you. But you also get a lot better protection with the SUSELinux profiles, so your security level is raised. If you have customized AppArmor profiles, then your situation becomes much more interesting. And then you have two cases. So either there's already an existing SUSELinux module that you can use. Then you need to check if your workload runs under that SUSELinux module. And with 440 profiles, the chances are pretty decent that something already exists there. If not, then if you want to keep the same level of protection, you need to write an SUSELinux module. And that is not trivial, unfortunately. There are tools that can help a little bit, but in the end, you really need to have a good understanding of your workload, and you will probably need some help by someone that has SUSELinux understanding. The alternative is, if your workload is not already containerized, it might be worth containerizing the workload at this point, because SUSELinux has protection for containers. And then you put your workload into a container, it will run under the normal SUSELinux protection for containers, and you don't have to have the specialized SUSELinux policy module just for your workload. If you disabled AppArmor until now, then please don't tell me that. I'm a security guy. I will not find that very funny. And in general, it's really not a good idea. These systems are valuable. They really help with security, so please reconsider if there's an alternative to that. I know that in certain situations, the pain of having to deal with these systems is not in a good relationship with how much gain you get out of these, but usually people reconsider after getting hacked for the first time. And if you already containerized your workload, then this will probably make your life a lot easier, because then you can just move it into this default protection that you get from the SUSELinux container module, and that is definitely helpful for you. If you then see problems with your containerized workload, then this is an indication that you are that you violated some best practices. Because normal container workloads should work fine in an SUSELinux environment. If your container does not work fine, then there's a chance that you did something that you probably should not do. So with that, thank you very much for your attention, and do you have any questions for me? Okay, yeah, then thank you very much for your participation. That was actually quite fun for me.